Hey friends, apologies for the interruption. We're picking up where we left off. Uh, I had taken a look at what we were doing on sheet 1. Now we're going on to the stuff that's on sheet 2. So let me go ahead and share screen there so that y'all can see what's going on. All right. So sheet 2 here has a collection of data. Uh, this is data that was produced using a normal distribution. And unlike the previous example, I'm not going to lie to you about what's actually done here, but there's a trick that I can make the computer produce a bunch of numbers that correspond to a normal distribution with a given average, that's the mu, and standard deviation sigma, okay? And so what we're going to do with this is to figure out whether or not this set of data came from that distribution. Now, I've told you ahead of time it does, but we're going to see how we go about in the sciences figuring out whether it's close or not, okay? So the essential idea is that you will calculate what's the chance, what's the probability that somebody could get the sort of numbers that we got here in this distribution um, just by random chance if the numbers, if the average and standard deviation are actually what's given, okay? So if you had a different mean and a different or a different standard deviation, then you would expect to get a set of numbers that are somehow different, okay? So anyway, notice here again, I have like 30 scores, and y'all will have more scores to deal with. I wanted to make sure that you could see all mine on the screen and stuff. But to figure out how many scores you've got, you can label it here and say what the n is equal to. And I'm going to right justify that. And remember how we do this? Equal, count. You got to think, is it counting alphanumeric stuff, or is it counting numbers? It's counting numbers, so you can just say count, parentheses, and we know it starts at A1. Now, mine I can see ends at A30, but you could go ahead and say A1000, because surely it ends before 1,000. And it tells me I had an error. I don't know if you can see the error screen or not, but I forgot to type the A before the A1000. So I'll put the A in there, hit enter, and it gives me a count back of 30. All right, and I'm going to left justify that so that it looks like it's together and stuff. Okay, the reason why you're going to need that is that you're going to do a calculation of several things here. And I think I'm going to put those in column F, and I'll go ahead and tell it to right justify all of them. But these things you're going to calculate are going to be what you use to determine the probability that you could get this set of data. So here I'm going to say that we're going to calculate X bar. So what X bar is an average that you take from a sample, whereas the mu was an average you took from a population. Kind of like, just for example, think about this as an example. If we talk about the average height of American males, it's you may be surprised to find out that the average height for American males is somewhere around 5'8", 5'9". And if we took a random sample, like, this is a random sample here, and it just so happened that that random sample included a bunch of athletes. Athletes tend to grow bigger, right? And so you might get an X bar from your athletes that was bigger than what your mu for all American males actually is. So that's the kind of thing that we're going to do in here. But we're going to figure out the X bar, and we're going to figure out S, which is a sample standard deviation. So we're given what the actual population standard deviation is, but there's a formula for figuring it out from samples. It's just slightly different. But we're going to go in here and we will say equal average, parentheses. We know it starts at A1. And since we got the count, there's 30 things there, we know that we can go ahead and stop it at A30. So same thing here, equals stdev dot. Now, it gives you the option .p for population or .s for sample. We have a sample. So we say .s, parentheses, and then you have to tell it the A1 colon A30 again. Okay. Yours will be different because you'll have a different number of data points. Okay. All right. Then the thing that we're going to figure out right here is going to be, I'll go ahead and write it as sigma divided by the square root of n. Okay. Now, this is something that we do in these calculations, and it just shows up in a formula somewhere. Okay. And we're going to need it in order to do our calculation. So we'll go ahead and label it. But I'm also going to do s over the square root of n right underneath that. All right, so sigma over the square root of n equals, I click on the place where the sigma is. Now, if I found out later that the sigma is actually something different, I could change where it's at and make that work. And square root of, and I'll click at the place where the n is. Okay, so that just does the calculation for you. Same thing here, equals, I'll hit the s, divide, oh, not that, divided by squirt, and I'll hit the n, and I'll let it do the calculation. All right. So what we're looking to calculate here is going to be the probability that our x bar would be less than or greater than this 47.87 stuff, right? So in doing that, we're going to use the normal distribution equals norm.dist, parentheses, and it shows you the little helper there. The x is going to be the cutoff place, okay? And then the mean and standard deviation are going to be taken from this other place over here, all right? So the cutoff that we're going to think about is that x bar. And then the mean is going to be that 50. And then the standard deviation, you may think it ought to be the 10, but because we're talking about the sample stuff, we're going to get it here with that sigma over the square root of n stuff, okay? And then you'll say cumulative. So before I hit enter there, let's think about this. If we know that the actual mean is 50, and the standard deviation, that means how spread out things are. If we know that standard deviation is 10, and we're talking about this x bar that's pretty close there in that 47.87 stuff, then we expect for the amount that is less than that 47 to be less than half, because 47 was less than the 50, which is right in the middle, okay? How much less? Well, that depends on how spread out it was. So I'm just going to hit enter, and it says it does not know what I asked for. So, oh, I typed the word cumulative instead of the word true. Okay, but it came back with a 0.12178. So about a 12% chance, right? And I should have labeled this. So I'm going to, over here on the other side of it, I'm going to say equals the probability that x would be less than X bar. Oops, X bar. Okay. And I've entered too few arguments for this function. Well, because it thinks I want it to be, okay. Turns out this was a bad choice. I should not actually put that on that side. I'm going to take and grab this and move it over so that I can say probability X is less than X bar equals. All right. And this stuff here, I'm going to tell it to write justify. Okay. Hopefully I'll see what went awry with that. I can't say equals and then the probability stuff because then it thinks that I'm trying to write a function. So instead I need to say the probability of that stuff equals, you know, okay. But like I said earlier, we get about 12%. So then here underneath that, I'm going to type probability that X is greater than the X bar equals. Now, the trick is that if you are doing a less than and a greater than, and it's a continuous distribution, they're just opposites of each other. So instead of having to figure it all out again, we'll say equals to let it know we've got a function, 1 minus that formula that was above it, okay? So if you had a mu of 50 and a sigma of 10, the probability that you would get a distribution like this, or less, that you get a distribution that was like this, or that had an even lower average than this, would end up being about 12%. The probability you'd have a distribution that would have some average that was more than this is about 87%. Okay, so what we have to think about though is the probability that we would have a distribution that was different. Okay, and so if you remember, prob X not equal to X bar. Okay, if you remember the way that we went about that in the other example, we tell it equals 2 times, and you want the minimum of those two up there. If you took the maximum, it would definitely get you something that was more than 50%, because, you know, either way, one of them is going to be more than 50%. And then when you doubled it, you'd get a probability that was more than 1, and probabilities are never more than 1. So we'll have 2 times the minimum, not the maximum, and we get about 24%. Okay, yeah, a little more than 24%. What good does that do you? So the conclusion that you're drawing here, you're looking to see if you have strong evidence that the distribution is that the distribution that you have is somehow different. So strong evidence means, is the probability that they're different going to be less than 5%? If the probability they're different is less than 5%, you have strong evidence that, sorry, I said that wrong. If the probability that you would get this at random is less than 5%, then probably something's wrong about your assumptions, okay? And so in this case, we have the probability is around 24%. You may hear dogs bark in the background. Sorry. Shh. So, because the probability is not less than 5%, then that says that you could have just random fluctuations that would make the X bar be as low as it is, you know, different from 50. Okay, so we don't have strong evidence here with this. Maybe in the data that you end up with, it might end up being strong evidence. Might after you multiply the minimum by 2, you might end up with something that was less than 5%, in which case you would say, I think that the distribution I got ends up being different from having a mu of 50 and a sigma of 10. And you base that on the p-value. Small p-values are strong evidence. Big p-values are weak evidence. So here, for example, 24%, quite a bit more than 5%. It's not much in the way of evidence. Okay. So in your write-up that you will do, your progress report, you're going to say something about how that runs. Okay. Now, I want to show you, in addition to that, another way that people often do stuff. This is referred to as a z-test. It may be the case, you might find out that the z-test is not automatically in your machine or in your installation. If that is the case, wow, okay, then you may end up needing to do a little bit of extra work in order to get the statistical analysis tool pack. Google that. You'll get some instructions about how to install that, and then go and follow those instructions. The machine I'm working on, as you might guess, because I teach math, has all that stuff installed on it. So yeah, I will try to remember to Google and find the link and just give that to y'all later on. Okay. But all right, anyway, the thing we're going to use is referred to as a z-test. If you go in here, I'm going to label this one as just z-test and not really say exactly what's going on with it, but I'm going to say equals z-test, this thing that's built in. And if you can read it there, it says z-test of array. So the array is going to be the group of data that you've got. And remember that for us, that's A1 colon A30. You might have something bigger on yours, right? And then the X value that we're talking about needs to be given to it. And that's going to be here, the 50. I wish that they had labeled that mu instead of X so that you'd know what's going on with it. And then comma, and it says something about using the sigma. And we're going to go ahead and choose this one here. That's the sigma over the square root of n. Okay. And we'll close parentheses and let's just see what we get back. We got 1. Well, that does not seem, it does not seem like we should be getting 1 out of that. As a matter of fact, the last time I did this, that's not what it came back with. So let me check my numbers here. The D2, is that the right thing? Yep. And then that G6. Goodness. Is it perhaps the case that my G6 needed to instead be the D4? It does. Okay. So if you take a look here, this 87, this 0.878 and so forth is the probability that X was greater than X bar. It will always be doing the right-hand part of it. If we look back here, I'm going to share screen. Well, I'm going to share screen, but it's got the wrong thing on it. Where's my Desmos on this? Gosh, I hope I don't have anything that has privacy issues or something. All right. So if you look at what's going on here, just illustration-wise, I'm going to draw the picture. It's 47 or 48. something like that. So the z-test is always going to take things on the right-hand end. If we'd gotten a value of that x bar like 60 or something, then it would take the area that goes to the right of the 60. But z-test is what's referred to as a right-tailed test. If you want to use it to get something that is a left tail, so that you're getting area like this, so 48, right? If you're wanting to use it to get the left tail, then you have to put a 1 minus in front of it. All of these things are assuming that you know all the details about how to use them and stuff. So, all right. In any case, though, we have something where we have the x bar we're getting is less than the predicted average, or the population average. And so we really wanted to think about a left tail. Okay. So that's the thing to keep in mind with what we're doing here. Z-test will always give you the right tail. So if you're wanting to work with it, you should have the z-test done and the opposite of it done. And then if you want to use what we refer to as the two-tailed test, I'm going to put a little label in here where it's to say z-test right, and then I'm going to put z-test left. Okay. The two-tailed, we're going to do what I did above equals 2 times the minimum of those two things. Okay. So with regard to this, if you're working with the statistical analysis tool pack, you may run into some extra distributions that have things like dot RT or dot LT for right tail and left tail, and dot 2T for two-tailed. If you figure out how to use those, you can skip a lot of the extra little stuff I'm doing here. But the thing that I'm essentially doing is getting the area of stuff that goes out one direction and this area of stuff that goes out the other direction, and then multiplying by 2, or multiplying one of them by 2 in order to get the area going out both directions at once. So, and you're always taking the minimum of the two, right? And okay, so a quick little change we're going to do here. So I'm going to move all of that down just a little bit. And I'm going to go ahead and label above this that is using sigma. Okay. We're going to do the same sort of stuff over here, only using S. So the thing of this is that when you do these sorts of tests that we're thinking about, that they you don't always know the actual value of sigma. And sometimes what you have to do is to substitute S for it. If you look at the sigma that I gave you, it was 10, and the S that we got from estimating it, 9.9495. That's pretty close, you know. And the thing that we generally find is the larger the n value is, the better that estimate turns out to be. So, all right, so I'm going to copy all that stuff down, and then I'm going to do the calculations. So remember that we were doing the normal distribution stuff. So equals norm dot dist parentheses. Man, you know what? It'd sure be nice if we had done that on the other part with named variables. And then you could save a lot of stuff by just copying things over and changing the one thing that's different. Unfortunately, we didn't. So, all right. So our probability, and it's that you have the x's, and that's going to be the x bar, comma, the mean, that mu, comma, the standard deviation. Now, this time we're going to use the s over square root of n, not the sigma over the square root of n. And then comma, the not cumulative, but the word true. Right? Notice that we got 0.120596 something or another. That's super duper close, right? But there may be cases in which you just don't actually know what sigma is, and you have to be happy with using S. The rule of thumb is that's generally okay to do as long as the n is 30 or more. There's certain other cases where you can do it even with small n values, but you have to know more. All right, so how did we get the probability that x was greater than x bar? That was just equals 1 minus the probability that it was less, right? And then how did we get from that the probability that x was not equal to it? We said equals, I have a bug. I have a bug that just landed on my monitor. Oh, shouldn't work at night. Okay, equals 2 times the minimum of those two things. And you just highlight them, let them go with that. And notice we got a very similar number. Likewise, we can come in here and say equals z-test parentheses. Now the x we talk about is going to be the array that we talk about is going to be the A1 colon A30 that we, whatever it was that you were working with. And then the x that appears in it, you're going to get with the 50, right? I should look back and make sure that I got the right thing there. And then the sigma, if you don't tell it what the sigma is, I'm going to go ahead and choose it here, right? But if you don't tell it what the sigma is, it should just go calculate the s and do the same thing as what we've done by hand here. Let's go ahead and do it by hand the first time and see what we get. We got 1. Well, that is pretty worrisome. I wouldn't have thought that it would be that nice. So let me see whether if I remove this, I get that same thing. I don't. Well, I do not have an answer for why it's getting something different on those two. Thrilling. All right, for the left tail portion of it, we are going to say equals 1 minus that thing up there. And for the two-tail portion of it, we're going to say equals 2 times the minimum of those two things. And so, and notice that if we use the sigma and do the two-tail test, we've got about a 24% chance, 24.4, something like that, percent chance that we could get a distribution like what we did. Whereas if we use the S instead, we get about a 24.1% chance. Both of those are more than 5%. 5% is usually our cutoff, right? And so we would actually make the conclusion here that, yeah, we don't have any strong evidence that this data did not come from the distribution with the mu of 50 and the sigma of 10. So that's that for what I want you to produce. Then I want you in your progress report to just detail this sort of reasoning, okay? And, talk about what you might find confusing about it, and that sort of thing, right? Okay, I'm not going to cut this apart into a third video. I am instead going to go straight into sheet number 3 in order to take a look at what we've got going on here. Now, as usual, I have a smaller list than what you will have on yours, but what I want you to do is to take a look and notice how it's produced. What I did was to take a function called norm inverse there, and can I make that bigger so that you can see it? Yeah, norm.inverse, and then I said rand. And what that's going to do is to randomly choose a number from a normal distribution that has a mean of 50 and a standard deviation of 10. This was the way I produced the data for the previous one, okay? But the tricky thing to notice here, oops, yeah, I don't need to make it this small, is that now if I do something else on this sheet, like type the number 1, boom, all of that data changed because it's recalculating random numbers over again every time. Now, that's going to be a huge pain for y'all if you're working it like that, okay? So what I want you to do is to take your data and highlight it. You know, as a matter of fact, you could just take your data and highlight the whole column. Copy it either by right-clicking or by hitting Command-C, Control-C, or whatever, and then we're going to paste it. And we're going to have to tell it to paste special. And for the paste special, there is a window that you can't see. I forgot about that. So I'm going to do the share screen so that you can see it. All right. So the paste special window has these choices here. You want to choose values, because now what it will do is to paste the values that had gotten from those formulas, and now it won't change when you do more operations to it. All right, hit OK, and it should have, I don't know what it's actually showing you on the screen right now. So I'm going to reshare in order that we can see that. All right. So now for me, we've got these 30 numbers here. For you, you've got quite a few more. One thing that you'll need is to know how many more. So equals count A1 colon A1000. And it told me I have 30 of them. So for the thing I need to do, I am going to need to take those numbers and I'm going to sort them. So, yeah, sort did not come up as an option there. So I'm going to hit escape and I'm going to have to go to where it says data in the menu and I'm going to choose sort. You could go ahead and just hit the A through Z on that, but I want to point out how that sort works. And that's going to bring up another one of those damn windows. Yeah, let's just do the A through Z sort. Okay. Now notice 31 will be the lowest and 68 will be the highest. All right. So you've got those numbers sorted there. The next bit that we're going to need to do, excuse me, it would be handy to insert a column to the left. And I'm going to have the numbers 1, 2, 3. You just need to enter a few consecutive numbers there, highlight them, use the little drag handle and drag down, and it should follow your pattern and count up to however many that you go down to, okay? Maybe you have 100 of them, you know, whatever. You need to drag down until you've got numbers for each of them, okay? All right, so then I guess I should maybe put some labels here. I'm going to right justify this column, and I'm going to left justify this one. I'm going to say here the n equals 30. Okay. And we're going to go ahead and figure out the x bar, and we're going to figure out the s for these. Remember how we did that on the previous page? So average of A1, 30, 30, and equals standard deviation dot s of A1 colon A30. Come on. So I'm going to go ahead and name that mu. That's going to make what I'm going to do next a little bit easier. Maybe a little bit of a pain if we had this defined as something else on the previous page. Sorry. All right. So what you're going to do in this column C here is to use the norm inverse. And I'm going to blow that up so you can see it. We'll say equals norm dot inverse. Okay. So rather than producing a random number using the rand function, we're going to take A1, that is the position that it's at, and we're going to subtract 0.5. I'll talk about why you subtract that here in a minute. Comma, and then we want to have a mean, which is the mu that we've just determined. The mu that it determined can't be right. We'll go fix that in a minute. And the mu of that and the sigma that is coming from that, right? And so it randomly produced there. Now, we're going to see the beauty of having this here. Okay. Notice how it says A1 to A30. I did the wrong thing. I should have said to take the average of B1 to B30. B1 colon B30, because I wanted the data that I had there. Similarly, the standard deviation is wrong as well. Okay. All right. But because we did things positionally there, it now has just gone back and fixed all that. So that norm inverse, that mu and that sigma for that probability. I'm sorry, folks. It is late at night and I have messed this up. Okay. Watch again as I fix it. Okay. So remember I said before A1 minus 0.5, and we'll talk about the 0.5 in a minute, divided by the count, which I did not go ahead and name, unfortunately. So that means I'm going to need to go back and put a $sign beside the 2 so that it doesn't get changed. All right. So the thing that's going on here is you're trying to get something from a normal distribution that corresponds to this position, okay? And the way you do that is to say, well, what would be the probability something would be to the left of this position? You know, it would be less than the numbers that are at this position. And so you have to say, well, what proportion of numbers are less than this position? Well, you would say 1 out of 30, you know, so the position 1 divided by the n. But if you do that, it's going to goof up something that we do later. And I'll come back to this in a second. So the reason that we subtract the 0.5 is as a correction to get the stuff, only the stuff that is less than this, as opposed to less than or equal to. All right, so then we had the mu and the sigma, okay? And you'll see that the number that it calculates for that is somewhere close to the actual number that we got, right? And then I'm gonna shrink this down a little bit so I can see it all at once. I'm gonna use that little handle thing and drag down here. And when you take a look at it, you should see that all the numbers you're getting, they're pretty similar. Not exactly the same, they're pretty similar. Now, the way that we're going to judge whether it looks like these numbers are pretty close enough is visually, right? Highlight those numbers. And then we're going to go to the insert menu, and we're going to find this little thingy I'm pointing at here. I can't make it bigger, but it should have a hover over label that pops up that says XY parentheses scatter. So what we're doing is what's referred to as a scatter plot. We're going to do a lot more of that on Monday, but for right now, we're just doing this. Look at the choices you have there. You want the first one, but look at the others. What the others will do is to draw lines between the dots in different kinds of orders, and it may try to smooth them out or something. So we just want the dots, okay? Now, down below, you also have the option of doing bubble charts. Bubble charts are pretty cool, but I'm not going to try to explain what's going on with those right now. That's just too much, okay? So we can see that it drew a chart here with a bunch of little dots on it. Here is the visualization thing. If those numbers lined up in such a way that's pretty close to a straight line, then this is probably normal distribution data. So if you need to see a line alongside it for reference, you can right-click on any of the dots and tell it to add a trend line, okay? So hopefully it showed you the menu on that. But with the added trend line, there's several options. You always want to leave it as just linear, okay? And you want to go down and take a look at some options at the bottom. There's one called display equation on chart that we'll want to mess with later. But for right now, mostly what you want is the display R squared on the chart, okay? And then I'm going to close this little window out. And I'm going to zoom in here, right? The reason I'm zooming in is so that you can see that the R squared value, 0.9806, that's very close to 1. That suggests that this data you've got is pretty much lining up on the line. And you can see that visually as well. Now, one question that's a very good question, and I don't have a good answer for. What is the cutoff? How do you decide, nope, this isn't good enough? Well, for something visual, if you can clearly see it's a pattern that is not a straight line and that it pulls away from the line in the middle, then you can say it's not good enough. For that R squared number that we turned up there, to say that this is not close to a straight line, that R squared value needs to be small. I didn't give a good answer, did I? Sorry. But what constitutes small? It depends on what industry you're working in. If you're doing something that's medical versus something that's engineering oriented, you'll just have to hear what is strong correlation and what is weak correlation. from actual professors in that field. I don't know what they are. To me, a strong correlation, I feel like an R squared value that gets less than 0.5, that's getting pretty weak. Okay. They, but the whole thing about where the cutoffs are for strong, moderate, and weak R, it varies. Okay. This particular thing, though, being 98%, that means that we've got things lining up on the straight line super good. Okay. So when you write this up or write up your progress report section about this, you're going to report back what the R squared value is, or maybe what the line looks like, and report how good you think it is. I don't have a hard and fast rule about that, and everybody's data will be a little bit different. So it's going to be me looking and seeing, did it seem like it was reasonable? And it's probably all going to be pretty close to a straight line because I produced it that way. It ought to line up. So anyway, so these have been 3 tricks. The first is about evaluating whether or not a proportion that you've guessed about is correct. The second trick was doing a data analysis to see whether or not the mean on something was significantly different from what you were given to understand that it was supposed to be. And then the third trick was looking at a set of data to try to determine, does it look like it's pretty close to being a normal distribution? Okay. I realize all these are separate tricks, but they're all things that come up occasionally. Okay. So what's your next steps after you've worked through all this? You are going to go ahead and upload the Excel spreadsheet into the projects section of things. And then in your progress reports, or maybe it's reflections, you're going to write the sort of things that we talked about here. Your probabilities. Is your p-value small, giving you strong evidence that it's different, or is your p-value large, giving you weak evidence? Same thing here, that R squared value, is the R squared close to 1, giving you strong evidence it's in a straight line, or is it close to 0, giving you weak evidence? You're probably going to get strong evidence in both those. So anyway, upload those, write about stuff in your progress report or progress reflection, and then go have your weekend. Okay. See you on Monday.